Hello, in this video, I would like to talk about Fourier cosine and sine series. But before we proceed, we must know this theorem, which is the properties of even and odd functions. There are 7 properties that you have to know. And the number one is the product of two even functions, and we will get an even. For example, let's say we have two functions. We have fx and gx, and let's say fx is an even function, gx is also an even function. When f multiplied by g, which is even multiplied by even, we will get an even. Same with the second properties, which is the product of two odd functions, means f is odd and g is also odd. When these two products are multiplied, and the product is even also. And C, the product of an even function and odd, so let's say f is an even and g is an odd. When even multiplied by odd, we will get odd. Properties of number 4, the sum or difference of two even function is even. Let's say f is even and g is also even function. When even plus or minus even, we will get even. And when the sum or difference of two odd function, we will get odd. According to this theorem, if f is even, then an integration of fx from negative a to a is equals to 2 multiplied by integration of fx from 0 to a. Okay, this is because, let's say our fx is x squared. So we know that x squared is an even function. And this is the graph. Okay. And this is our limit from negative a until a. If we integrate x squared dx from negative a until a, we will get the area under the curve. So if you can see, since x squared is an even function, we know that it is symmetric about the y-axis. Therefore, if we integrate this function, we will get area, which is, let's say the area here is b and area here is b. Therefore, we can say that the area is equals to 2b, or we can say that the area is 2. We can just integrate from 0 until a x squared dx. Okay, this is what the theorem said. And g, if f is odd, then an integration of fx from negative a until a equals to 0. Okay, for example, fx is equals to x cubed. So we know that x cubed is an odd function, and the graph is something like this. Okay, it must be symmetric about origin. So if we integrate x cubed dx from, let's say we have negative a until a. So if we integrate this, we will get the area under the curve. If you can see here, the area of the positive and the negative is the same. Okay, sorry about my drawing. But since the area here is, let's say, b, and the area here is negative b, therefore, when we added these two area, b plus negative b, therefore we will get 0. So that's why this theorem said that if f is odd, if we integrate an odd function from negative a until a, we will get 0. Okay, before we go into Fourier cosine and sine series, you have to know these properties. Before we go into Fourier cosine and Fourier sine series, we must know that a Fourier series, which is fx is equals to a0 over 2 plus a summation of an multiplied by cos n pi x over l plus bn multiplied by sine n pi x over L, where our a naught here is 1 over L integration of fx from negative L until L, and this is our an 1 over L multiplied by integration of fx multiplied by cos n pi x over L, and this is our bn is equals to 1 over L and integration of fx multiplied by sine n pi x over L. Okay, so we will going to use this in our Fourier cosine and Fourier sine series. In Fourier cosine and sine series, let's say if f is an even function on the interval of negative L until L, then we can say that a naught is equals to 1 over L, again this is come from the Fourier series, is equals to 2 over L 0 until L fx dx. This is come from the Fourier series as I've mentioned earlier, and we will get 2 over L from 0 until L, and this is come from the theorem, which is theorem F. Next, our an is equals to 1 over L from the Fourier series, which is integration of fx cos n pi x over L dx is equals to, again from our theorem, 2 over L, which is from 0 until L, fx cos n pi x over L dx. Because since our f here is an even, and we know that cos is also an even. When even multiplied by even, so we will get an even function. So an integration of even function, we will get a double of integration from 0 until L instead of from negative L until L. Next, let's look at Bn from Fourier series. Said that Bl is equals to 1 over L integration of fx sine n pi x over L dx. But now, since our fx here is an even, if even multiplied by odd, sine function is an odd, so even multiplied by odd, we will get odd. And if we integrate an odd function from negative L until L, we will get 0. Therefore, our Fourier series for f, which is an even function, is equals to a naught over 2 plus summation of a n cos n pi x over L. Yeah, that's it. We don't have to plus bn here because bn sine n pi x over L, since our bn is equals to 0 and 0 multiplied by anything, we will get 0. Therefore, this is our Fourier cosine series. Now, let's look at what will happen if our f here is an odd function on the interval of negative L until L. Therefore, our a naught is equals to 1 over L from negative L until L fx dx. Since our fx is an odd, therefore an integration of odd function from negative L until L, we will get 0. And this is what the theorem in the properties of number 7 said. Same with an. An is 1 over L integration of negative L until L fx multiplied by cos n pi x over L dx. Since our fx is an odd and multiplied by an even function, cos is an even, so odd multiplied by even is an odd. Integration of an odd function from negative L until L, again we will get 0. But for our bn, 1 over L of fx sine n pi x over L, since our f here is an odd and sine function is an odd also, therefore odd multiplied by odd, we will get an even. So an integration of even function is equals to 2 over L from 0 until L fx sine n pi x over L dx. Therefore, our Fourier series, where if f is an odd function, a naught over 2 plus summation of a n cos n pi x over L plus b n sine n pi x over L, where our a naught is equals to 0, a n is equals to 0. Therefore, we will have into a summation of b n sine n pi x over L. And this is called Fourier Sine series.